Hello everyone, thank you for coming by. Today I'll be defending my thesis, so it's the star formation rate in the multiverse and the coincidence problems. First, a brief general plan. I'll first give the general background so that we have an idea of the context in which the work is based. Then I'll give the aim of my work and the methods that we used in order to solve that problem, the results that we got, and finally an outlook, so what could be done in the coming, after this, in this direction. So for the general context, there is this fine-tuning problem. So there is this idea that if we just change one of the many constants, so can I close the? If one changes just one of the constants in the universe, then the physics would be changed drastically, and possibly life would not appear. So, for example, Tegmark and company, they no. I'm sorry, I added the frame a bit later, so it's not there. But basically, it's just saying that it's listing about 26 constants that appear in the Lagrangians for particle physics. And if we change one of those, then physics would be very different. So there are four possible answers to this problem that are given by that are listed by Tegmark in his paper. Dimensionless constants, cosmology, and other dark matters, which I highly recommend if you have the time to read. So the first one is simply to say that everything is random, meaning that there is nothing deeper in this in the appearance of certain constants or certain values, which is not very satisfying for pattern-seeking mammals such as myself. Then there is a possibility of a multiverse, which is to say that there are many different universes, and we just happen to live in one where life is actually possible. Then there is the idea of design, meaning that our universe is created or simulated with certain parameters that allow for life, which again is not very satisfying from the physical point of view. And finally, there is the fecundity answer, meaning that life will appear no matter what. So no matter if you change the cosmological constant, if you change gravitational constant, then life will find a way to appear. So if we look at our own planet, it's not so absurd because life does appear in very harsh environments as well. But so the answer that we will be focusing on is the second one, the multiverse option. And Tegmark, in a paper called the Parallel Universes, which I also highly recommend, is he lists 4 different levels of multiverses. So the first one, which is the most intuitive, I would say, is regions beyond our cosmic horizon. So we live in a universe, and the visible universe is limited by the Hubble radius, basically by the speed of light, let's say, and the time the universe has had to grow. So for our universe, it's more than that, but it's, let's say, 14 billion years. And beyond those regions, there could be, there is actually more, the universe keeps on going on. And so beyond those universes, the initial conditions could be different, the physics could be different, we don't know. So that would be the first one. Then there is the idea of a post-inflationary bubble. So I'm just going to check. So post-inflation bubbles, which is, so the theory is that of chaotic inflation. So in our universe, inflation has stopped. So it's inflation is a period of very fast expansion of the universe. But the idea of chaotic inflation is that each time inflation stops in one place, it starts in another one. And so in each of these bubbles, there is a new inflation that takes place, and it's a chain reaction. So you're getting infinite universes out of this process. Then there is the many worlds of quantum physics, which is Everett's interpretation of quantum mechanics, which is to say that every time there is a quantum process which has different random outcomes, which has different random possibilities, actually each of these are realized but in different universe. So you get a new branch with each new outcome, let's say. And then there is the most abstract one, which is completely different mathematical structures. So we could imagine a universe with a different topology, with different dimensions, with different physical laws, etc., etc. Basically anything you can think of. So this is neatly resumed in this figure. So the level 1, as I said, this is our observable universe, but beyond this, we don't know actually what's going on. So we could have other physics going on, other initial conditions at the very least. Then there are those post-inflation bubbles. Time goes in this direction, and so each bubble represents its own universe. This would be, for example, our universe. It branches off every time. Then there is a many world of quantum physics from Everett, which is just, as you can see, this is flat space, this is our universe, and it branches off into different universes. And finally, there is this most abstract one, the mathematical structures, and you can imagine anything. So you have the Mandelbrot sets, you have a sort of curved space-time, but also closed space-time, so hyperbolic, closed, and basically anything is anything you can think of mathematically is possible in this interpretation. Okay. So that would be for the multiverses, and now for the coincidences in physics. Well, we don't like coincidences in general, and if we see a coincidence, then we think that there is something more going on. For instance, if we look at the mass of the sun, in our solar system, it's 2 times 10 to the power 30 kilograms. But if there is a very narrow range for which this would be. So the range of mass for the sun is between 1.6 and 2.4 times 10 to the 30 kilograms, which would allow for life. And anything outside that range would be either too hot or too cold. So this is a very strange coincidence. And actually, this would imply the existence of other stars, because otherwise it would be just strange. And indeed, observations have shown that there are other stars. And so now sorry, I added it later. It's not on the drive, but there are those. Maybe I'll show another one. Yeah, if we look at this graph, so normally the star formation peak should be aligned, just about aligned with this intersection, and the recombination should be aligned with this intersection. And there is one that is missing, which is the, I'm sorry about that, it should be the recombination that should align with this equality. So, so the 3 solid lines represent the energy densities in the universe. So the cosmological constant, the baryonic energy density, and this is actually, it should be gamma, and it's the photon energy density. And as we see, the redshift at which baryonic and cosmological constant are the same is about the same as when the as for the star formation rate peak. And for recombination, it's when the photon energy density and the baryon energy density is about the same. And there is one line that is missing here that should be re-ionization. That's when the universe comes out of its dark age, and it aligns pretty closely with the redshift when photon energy density and cosmological energy density are the same. So there are those three, there should be three, there are only two that are shown, and the two that are shown are the ones that I'll be investigating in this work that I have been investigating. Okay, so where was I? Yeah. Okay, so that's the aim. It's those coincidences and the methods. There are not many analytical solution for the star formation rate. So all we have are fits to the data, and they are very close. They don't allow for great variations, which is what we were interested here. So we decided to use numerical methods, and there was a code that was provided by Busso and Leischnauer that was already simulating the star formation rate, but not with the same parameters, but I'll come back to that. So we get the star formation rate peak with our code, and then with NASA's website, there is a web interface that lets us get the recombination time as a function of cosmological parameters. Okay, so the star formation rate from Busso and Leischnauer is this big function. There are actually three terms in the function. There is this f, which is the cumulative mass function from the Preston-Chester formalism, and this is essentially the star formation rate for different halos. Yeah. So the cumulative mass function f is derived in the paper. I don't have time to go in details, but essentially this delta C is the critical density at which a halo will collapse on itself. It's computed by considering the spherical top-hat collapse of a halo. And this sigma function is the variance in the linear theory. So it depends on mass and time, and Busso and Leischnauer decompose it in a function that depends only on mass and one that depends only on time. The reason for this is that the growth of the variance is linear, so it's very convenient to separate it this way. The growth function is obtained by solving the differential equation for overdensities. And so this is the general formula for the variance. This is the Fourier transform of the top hat, and P of k is the power spectrum. So it's Zeldovich, so it's k to the power of ns, where ns is the scalar spectral index. In our universe, it's about 0.96, so we know that the growth of structure is not completely scale invariant. And we have to multiply it with a transfer function to get how the energy is transferred from photons to baryonic matter at decoupling. Okay. Yeah. In the code, I implemented this growth function, as you can see. So there is this minus 2 times Hubble. Hubble is this h over here. So the way it solves it is you take the term that is second order and you put everything else on the right side. And so that's what you have. You have this minus 2 times Hubble times the Hubble function, Hubble parameter, plus 4 pi times rho at equality. So the code starts at equality, and our initial conditions are given at equality. So this u0 is the value of the growth function at equality, given in Boston-Eichauer, and du0 is its derivative. So those are the initial conditions. So just to come back quickly, so now we know what this function is, and we need still this gravitational collapse time, T graph. Formally, it can be computed by considering Birkhoff's theorem, which tells us that a region of space that is overdense by a certain amount will have the same cosmological constant as the background universe, but it will evolve with a different matter energy density. And so this h squared is the scale factor, the derivative of the scale factor over a. And when this the region is going to expand, and then at some point it will stop expanding, and then it will collapse on itself. When it stops expanding, it means that the acceleration is equal to 0. So formally what we do is we set this equal to 0, we solve, and we get a virialization density, virialization time, and from this we get the virialization density. But in the code we are using a fit, because it takes, otherwise it's a bit costly computation. So yeah, it looks like this. The fit is taken from again, Tegmark and company, and it depends only on the cosmological constant. So it's just a polynomial fit. Okay. So the star formation rate for a single halo is given by this formula in Boston-Eichauer, meaning that T graph is the gravitational time for collapse at a given time, and MB is the baryonic mass in the halo, because it's actually the baryonic mass that contributes to the formation of a star. And we can write it as FB times M, where FB is the portion of baryonic mass in the universe. In our universe, it's about 1/6. But we are going to vary this parameter as well. Yeah, so that's the star formation rate for a single halo. To get the star formation rate for halos of mass m, we have to integrate over all possible masses and multiply with the probability that it would have collapsed already. So this probability of collapse is taken from a paper by Lacey and Cole, and they define it as, so they say that a halo has collapsed when its mass has doubled, because at that time it becomes indistinguishable from the rest. So the computation is a bit long, but essentially we have to take the derivative of this beta function, where g is the growth factor, the linear growth factor, and s is this variance that I talked about earlier. Okay. Yeah. So P is a cumulative mass function, cumulative probability distribution, and so in order to get the probability itself, we have to derive it with respect to time. Okay. Right, so that's the star formation rate. If I come back just to show you the function, that's the whole thing, and now we're going to modify it a little bit. So in Busso and Leichenauer, what they use, the parameters that are being varied are the cosmological constant, lambda, the curvature of the universe, k, and the amplitude of primordial fluctuations, q. So the inflation field gives a Gaussian distribution of fluctuations, and these are of the order 10⁻⁵ in our universe, and this is something that they are modifying, but we are not interested in that for our problem. So what we would like to modify is the Hubble constant. So small h is the reduced Hubble constant. It's just h over 100. That's essentially it's the same. Then there is the omega matter, the total content of matter in the universe. We can also modify omega b, which is the baryonic content of matter in the universe. And we can modify omega lambda, the energy content of the cosmological constant. So the dark energy constant. Okay, so if we are to modify omega m, the equality density is going to be changed consequently as well. And so the way we computed it is we considered first the energy density of radiation. So here it's just a black body radiation. The one comes from the photons, and the 21/8 comes from the 3 types of neutrinos in the universe. But yeah, essentially a bunch of constants times the temperature to the power of 4. And from this, and for the matter, we wanted to be dependent on the temperature only as well. So what we did is we used this variable xi, which is the energy density of matter over the number density of photons, and both decay as a to the power of 3. So that means that this quantity is actually a constant. So if we fix rho m at a given time, then we have psi, and so we can get rho m as a function of the temperature only. So because psi is fixed. And so the temperature of equality is the temperature when those two things are equal. So we solve this, and finally we get the equality temperature as a function of psi only. Zeta is the Riemann function, but that's not so. Okay. So that was for omega m. And something else that we wanted to do is consistently changing the time. So we decided to define today as whatever time corresponding to a temperature of 2.725 Kelvin. In our universe, the temperature of the CMB is well, it has this value today, after 13.7 billion years. And so we wanted to define this and say that whatever time corresponds to this temperature will be today in another universe. From this we get, so the radiation density will always have this value today in the universe at T0, and we should be careful to modify the radiation energy density consequently, because if we modify the Hubble constant, then we are also modifying the radiation energy density, the radiation energy content of the universe. Because if we make it, let's say, 100 times smaller, the radiation, omega rad in our universe is 10 to the minus 5, something like that. And so if we make H0 100 times smaller, 100 times smaller, then we're making omega rad 10,000 times bigger. And so omega rad is going to be of the order unity, and we have to take this into account when we are modifying the parameters so that it stays consistent. So we know, so this is the Friedman equation in matter and radiation and cosmological constant dominated universe. And so we can solve this for A, and this will then give us the evolution of the Hubble parameter as a function of time. And whenever this equation, for whatever time this equation has the value h0, we're going to say that this is the time today in the multiverse. I hope that's clear. So that's just solving the differential equation for A for the scale factor. If we compare, we have A dot over A squared, so we multiply by A squared, take the square root, and finally we are left with this figure. Yeah? And so for first order differential equation, basically. So here are some plots of the time of t0 as a function of, here it's a function of the reduced Hubble constant. So in our universe, the reduced Hubble constant is about 0.67, so it will be somewhere here, let's say. So about 13 billion years. And as you see, if you make it a lot smaller, then today is going to be a lot later because the expansion of the universe is going to be a lot slower. So that makes sense. And similarly for the time today as a function of the matter content in the universe. In our universe, it's 0.315 as given by Planck. And so this corresponds roughly to 13.6.7 billion years. So that's the time dependence. So the today dependency as a function of omega. And so now that we know T0, we can enforce that the variance at 8 megaparsecs be equal to 0.811, just as in our own universe, because from measurements we know that the variance in our universe is 0.811, and so we're going to say that it's the same in every universe. I don't know if I have time for the problems, so I'll go straight to the solutions rather. So modifying omega n, I have included, so maybe it's not so easy to see, but so on top is a plot of the star formation rate. And on the bottom are the coincidence problems about which I talked a bit earlier. And so what we want to see is the behavior of those coincidences. Here is a plot for omega n is equal to 0.115, so it's smaller than in our universe. And so this is in our universe, it's the concordance model. The star formation rate peak is at, it was computed to be 1.8, which is 1.7, which is a bit lower than the actual one, because the program is not perfect either. It's an approximation. So yeah, already in the program the coincidence is a bit shifted to the right, it should be actually on the left because it's not so precise. And yeah, so basically, if we are modifying omega m, we are modifying the recombination time, but what we did here is that the baryonic matter content was not changed, and neither was the radiation content. So, sorry, it should be gamma, the photon content. So that this coincidence doesn't change, but omega m, but the recombination gets a bit closer to, gets a bit smaller when we increase omega m. It's a bit hard to see on the plots. Yeah. Now modifying the Hubble constant, it's plotted in increasing order. So this is 0.2, this is 0.67, and this is 1, because we were actually limited by the web interface of NASA, which could only take values between 20 and 100. If I put something bigger, he was always asking me if I was sure about my input data. So what we see is that the star formation rate peak gets shifted to the right. All the solid lines don't change because rho lambda, rho b, and rho gamma don't depend on age. So those are fixed. But the star formation rate peak is moving to the right, and the recombination redshift is moving to the left. No, I'm sorry. Actually, rho b and rho gamma do depend on H0. Let me see that maybe better in the plots, in the tables. Then there was a modification of omega m, keeping the baryonic matter content fixed. So what that means is that in our universe it's about 1/6, and so what I did here is that I changed omega m. I made it so it gets bigger and bigger, but I enforced that the baryonic matter content stay the same. If we say that omega m is equal to 1, then for this plot, omega m is equal to 1, and in that case, omega baryon is going to be exactly 1/6. And as you can see, the star formation rate peak moves to the right, but the equality does not follow for baryonic and cosmological constant, and neither does it for recombination. So recombination is actually moving to the left. If you look here, it's a bit right, and it gets closer to 10 to the 3. But the equality is actually moving further and further away. So again, no correlation between. Okay. So this is a table of all the values. Where we can maybe see a bit better because the variations are not so big. So this is if we are varying only omega m. So omega m goes from, I made it change from 0.115 to 0.815, and the star formation peak gets bigger and bigger, but the equality time gets smaller and smaller. And similarly for recombination, the redshift of recombination gets bigger and bigger, but the equality density, the equality redshift does not move at all. So again, there is no correlation between recombination and equality, and there is negative correlation actually between the star formation peak and equality. The table 2 is a summary for the variation of the Hubble constant. So as I said in the beginning, when we are modifying the Hubble constant, we also have to keep in mind that we are modifying the radiation energy density, and therefore we are also changing the energy content of radiation. Gets so the smaller h, the bigger omega gamma, and therefore also the equality between OB and between baryonic and photon energy density is going to change. It gets bigger and bigger, but the recombination redshift gets smaller and smaller. So again, negative relation. And what else? Yeah, the star formation peak gets bigger and bigger, but the equality between baryonic and cosmological constant doesn't change at all. So no correlation. So that was for those two, and then there is varying the matter content, keeping FB, so the ratio fixed. And so for the first time, actually, there is a positive correlation. No, still no, it was for this one. So here there is again no correlation, negative correlation between both, because the star formation peak gets bigger and the equality gets smaller, and the recession gets, the recombination gets smaller, while the other redshift gets bigger. And yeah, so the only time I got a positive correlation was when varying only FB, so the ratio between dark matter and so the ratio between baryonic matter and dark matter. And so if we change only that, with all the rest being just the concordance model from Planck, we get that the star formation rate peak gets smaller and smaller, and also the equality between baryonic matter and cosmological constant. But unfortunately, for the recombination time, it's not. It's again negatively correlated. So yeah, coming back to the problem of coincidences, it would seem that we are lucky enough to be in a universe where this happens to be at the right time, and therefore to permit the emergence of life. And so this would probably be a strong hint for actually the existence of multiverses, just like having a star with having our own sun with a certain value implies the existence of other stars in the universe. Probably that having a universe that has those right coincidences implies the existence of other universes. Yep. So for the outlook, so what we could do from here on. Sorry, this should not be there. It's only compute. So we could compute the third coincidence problem. So the coincidence between the reionization and equality between cosmological constant and baryonic matter, and photon energy density. I'm sorry. And we could then see what happens if we modify more fundamental parameters. So if we change for example, the electron charge, how that would change. So that would change the quantum cross-section, and it would then change the thermal history of the universe. So that would also be interesting to see what happens. And then the first stage would be to modify the laws of physics themselves. So, if we recall this this graphic that I showed at the beginning, this one. Sorry, I have Yeah, voilà. It would be modifying, so going to a completely new, different mathematical structure. That is more ambitious than what I was able to do in the frame of my thesis. So, yeah, I thank you for your attention. If you have any questions, I'm staying here.